Hi everyone, we're the Boundary Element Method group. I'm Sandra Ike.
I'm Tong Ge Zhao.
I'm Guanzhou Chen. Here is our presentation. Our presentation contains 7 parts, and first is introduction, historical perspective, general principles, governing equations, hand calculation example, numerical example, and example applications. The first part is the introduction. The boundary element method is a fully equipped numerical technique to solve linear partial differential equations, widely applied in many engineering areas. This picture shows the modeling in corrosion using boundary element method. The idea of the method. The boundary element method tries to use the given boundary conditions to fit the boundary values into the integral equation, instead of using the entire space defined by the partial differential equation. Once calculated by this way, in the post-processing phase, the integral equation can be used to directly compute the numerical solution again at any desired point in the internal solution domain. Comparison between FEM and BEM. FEM needs the discretization of the whole domain, but BEM only needs the discretization of the boundary. FEM is solvable in most linear second-order PDEs, and BEM is maybe unsolvable for homogeneous and nonlinear problems. FEM is more precise in finite domains. BEM is more precise in infinite or semi-infinite domains. The picture below shows that to model the same domain, BEM needs less element than FEM. The advantages and disadvantages of BEM. Less data preparation time because of the less data BEM needs, and high solution of stress, less computer time and storage of the less data, less unwanted information. But it has some disadvantages of unfamiliar mathematics because it uses different method of FEM and the modeling for interior in nonlinear problems, and fully populated and unsymmetrical solution matrix. And for scene structure 3-dimensional analysis, BEMs not work that well.
Historical perspective. BEM has a rich heritage which can be traced to its mathematical foundation in the late 18th century, from Laplace equation, the existence and uniqueness of solution of boundary value problems, Gauss and Stokes theorem that allowed reduction in spatial dimension, Green's identities and function, the Fredholm integral equation, and the extension of Green's formula to acoustics, elasticity, and other physical problems. These are foundations that I can say led to the birth of BEM. Boundary element method can be divided into two, direct and indirect boundary element method. Judge Green set up the basis for the direct method, and then Frederick Holm contributed to the theory for the indirect method. There are many pioneers whose contributions are key to the mathematical foundation of boundary element method, also known as BEM. The first I'll be talking about is Enrico Betti. He made an important step towards deriving Green's formula for elasticity when he introduced the reciprocity theorem. His work also inspired the two people which are below him, Volterra and Sominglina. I'm sure I'm messing up their names. Vito Volterra and Carlos Sominglina. And his work, Enrico Betti's work, was an inspiration for their work. And their work, Carlos Sominglina's work, Vito Volterra's work, can be directly applied to obtain BEM formulations. There is a pre-computer era and post-computer era for BEM. In the first half of the 20th century, early numerical methods were attempted before the invention of electronic computers. Scientists like Nikolai Mashkelishvili and Theodor von Karman made attempts to find approximate solutions of boundary value problems using boundary or boundary-like discretization. However, without the aid of computing tools faced the drudgery of computation, and thus there was a hindrance to the further development of these numerical methods. Numerical methods could not truly prosper until the invention of electronic computers in the 1960s. So the electronic computer era. Several independent methods of experimenting on boundary element method emerged in the 1960s. M.A. Joswin and A.R. Punter in 1963 formulated 2D potential problems in terms of a direct boundary integral equation and solved it numerically. A turning point that marked the growth of numerical solutions of boundary integral method was when Frank Rizzo published an article, An Integral Equation Approach to a Boundary Value Problem of Classical Electrostatics. Rizzo applied a numerical method for solving the Somiglina identity for electrostatics problems. If you recall, we spoke about Somiglina, whose methods can be applied to BEM formulation. Rizzo's work has become known as the birth of direct boundary element method. The last person I'll talk about is Carlos Alberto Berbia. In the late 1970s, BEM experienced exponential growth. In 1978, Berbia organized the first international conference on BEM at Southampton University. He also published the first book on BEM titled Boundary Element Method for Engineers.
Next, I will talk about the general principles. Let's start with the two-dimensional Laplace equation. Phi is a function of both x and y. Look at the figure. Closed curve C containing C1 and C2 is the boundary of region R. On C1, phi is specified, and on C2, the phi over dn is specified. How can we solve this equation? To solve the equation, it will be much easier if we use polar coordinates. And we can rewrite Laplace equation as the second equation here. Then reduce it to the ordinary differential equation as the third one, and integrate it twice. We can get the general solution, where a and b are arbitrary constants. Finally, rewrite it to get a particular solution. If we make a equal 1 over 2 pi and b equal 0, and shift the center from 0, 0 to the general point psi eta, we can get the third equation, which is very important of the development of boundary element methods for the numerical solution. We can use an uppercase phi to write it as a fundamental solution, which is also named the free space Green's function. Applying Green's second identity, finally we can convert the double integral over R into a line integral over C. It can be used to derive a boundary integral solution for the two-dimensional Laplace equation. After a series of derivation, if psi eta lies on a smooth part of C, we can obtain this single equation, where lambda is defined by this way. Together with the boundary conditions I have mentioned, a numerical procedure can be obtained to determine the annual psi and d psi over dn on the boundary of C.
Next is governing equations. First, we introduce mass balance equation. And for 1D problem, phi equals to 1. And solve for the equations, we got the final result. Then we introduce Darcy's law, and it can be also written in terms of V, and plug it into the mass balance equation. We got our result. Then, as we know, the governing equations for fluid flow in wells. We assume that it's homogeneous and isotropic media and slightly compressible fluid. The equation can be rewritten as. Then, simplify the equation we got. We have our result, and Q is a sync term for production well. Then add dimensionless variables to the equations, and replace them with the values in the former equation. And then we got the equations below. Then we introduce Green's function, and using differential operator L to the equations we got. And then using G as a fundamental solution to the differential operator. Next, combine our result with Green's second identity and Gauss' theorem. We got the equation. And this equation can be applied within the domain. PD and partial PD partial N can be specified as boundary conditions in most calculations. And then we get the general boundary integral solution for boundary element method, and beta equals 1 if the point is inside the domain, and beta equals 0.5 if the point is on the smooth boundary.
Hand calculation example. We'll now use BEM to solve a 1D problem of Laplace equation. The governing equation is given below. We'll consider 3 cases of boundary conditions: Dirichlet boundary condition, Neumann boundary condition, mixed boundary condition. In the above boundary condition cases given, U is the primary variable, X is a field point, dx is the neighborhood of X, or the differential element at X, U of X is the primary field, V is the secondary field, K is a constant coefficient which equal 1 in present cases, and V of X is the secondary field. We'll solve this using BEM methods step by step. Stage 1, we'll find the fundamental solution of the governing equation. The fundamental solution of U of X, x bar, is a function of X with a parameter x bar defined as -1/2 minus x bar, the absolute -1/2 times the absolute value of X minus x bar, which satisfies this condition. X, the second partial derivative of x bar with respect to x squared, is equal to delta x minus x bar. This is a Dirac delta function. The Dirac delta function is a very useful tool in applied mathematics. It's a function that is 0 everywhere and except at one point, and at that point that it's not 0, it's infinity. The Dirac delta function also integrates to 1. Okay, also we define V of x bar as the partial derivative of U of x bar with respect to x is equal to 1/2 minus h x minus x bar. This is a Heaviside unit step function. It's also an important tool in applied mathematics. It takes the value of either 0 or 1. Stage 2, we derive a formula of two-field variable which converts domain integrals into boundary integrals. After integrating by parts twice, we yield a 1D version of Green's second identity. Then the next stage, we obtain a boundary integral equation for a domain point. We do this by substituting the governing equation and also the condition that satisfies the solution for the boundary equation into equation 1.8, and we yield this negative U x bar is equal to, we yield this equation right here. And then upon exchanging, interchanging the barred and unbarred symbols, we obtain this equation, and we introduce the symbols, the small letter v and capital V, as defined in previous slides to yield this. Where u of x bar x is equal to negative 1 over 2 times the absolute value of x bar minus x, and v of x bar x is equal to the partial derivative of u of x bar x with respect to x bar is equal to 1 over 2 minus h times x bar minus x. Next, we will let our x approach the boundary and obtain the boundary integral equation for a boundary point. So as x approaches the left boundary point, we have the limit of u of 0x as x approaches 0, and that gives us 0. The limit of u of 1x as x approaches 0 gives us negative 1 over 2. The limit of v of 0x as x approaches 0 is equal to 1 over 2. And the limit of v of 1x as x approaches 0 is negative 1 over 2. And as x approaches the right boundary point, we have the limit of, as x approaches 1 for u of 0x gives us negative 1/2. The limit as x approaches 1 for u of 1x gives us 0. The limit as x approaches 1 for v of 0x gives us 1/2. And for v of 1x, the limit as x approaches 1 gives us negative 1/2. And so now we have the boundary point, the left boundary point at x equal to 0, the boundary equation is given as this. And for the right boundary point, x equal to 1, the boundary integral equation is given as this. And so our next step is to choose a finite number for the boundary point, discretize the boundary integral equation for the boundary point, and also put the discretized boundary integral equation in the matrix form. For 2D and 3D problems, the boundary integral have to be discretized first. However, this is a 1D problem, so no discretization is needed. And so what we're going to do is rearrange the previous equation, which we have from previous slide, into a matrix form. And then we use the boundary conditions which was stated in the problem for each boundary case, Dirichlet, Neumann, and the mixed boundary conditions. We use it to solve the matrix equation. And so for case 1, we have the Dirichlet boundary condition. We set it up into a matrix and we solve this, if you recall from linear algebra, how to solve a matrix. The answer you get, the solution we get is this. And for case 2, we use the prescribed Neumann boundary conditions. We also set it up into a matrix form, and solving the matrix, we also get this solution. We repeat the same process for the case 3, mixed boundary condition, set this into a matrix form, solve the matrix, and we obtain this solution as well. And finally, we solve for the domain point by using boundary integral equations for a domain point. From equations 1.10 and 1.12 from previous slides, for the domain point 0, 1, we have this matrix equation. And when we consider the three cases, Dirichlet, Neumann, and mixed boundary equations, we obtain, solving the matrix, we obtain these solutions, and these solutions are identical to the closed form solutions. So these are the boundary integral equation solutions.
Now, let me introduce a numerical example. This is a typical fluid flow problem, the driven cavity problem. Now, consider a two-dimensional square box, as shown in the figure, which contains viscous liquid. The lid of the box moves at a prescribed speed u in the x direction, and the fluid velocity on the remaining walls of the box is 0. The length of each cavity wall is equal to 1. For convenience, I will use L for the lead and W for the walls in the following process. I got the final results by using the method of Dr. Mark Bliss BEM code for Stokes floor, and the governing equation is two-dimensional boundary integral equation that I have mentioned before. This is a basic procedure to solve the problem. First, I set 64 boundary elements, that is 16 elements on each wall or lead. And then I computed the wall tractions to determine the fluid velocity at any point in the floor. Finally, I determined the streamlines. This is a part of the main MATLAB code I used to solve the problem. I will show you the plus of the results. First of all, this is the cavity with 64 boundary elements. The second one is the computed tractions. We can see the sharp spikes at the corners because of the traction at a 90-degree corner in Stokes floor divergence. This is a property of the floor field. These are velocity profiles of horizontal and vertical directions along x equal 0.75. The last one is the computed streamlines.
Example applications of the boundary element method. One application is acoustic levitation. Another example application is the application to incompressible laminar viscous flows. And BEM also can be applied to crack modeling. And here are the references of our presentation. Thank you.